welcome to the Women in Tech Introduction to Machine Learning workshop with QuantumBlack and Researchers Code. I'm Victoria Carr, and I am founder of Researchers Code. So what is Researchers Code? So we are a community in London that supports women in tech academia. So this came about a few years ago when I was going to a few tech events, and I thought it was quite industry focused, and there are a few academics there who felt like they weren't part of the community. So we decided to start a community that focuses on showcasing the talent of women and diversity in computational sciences, from academia to outside of industry. And so this is how we do it. So we run workshops and events monthly that helps upskill people who are interested in tech or who work in tech or in academia. So we previously had workshops such as Introduction to Linux with Azure. We've also had workshops that teach you how to write Wikipedia articles. So we have a demo at the Welcome Collection. We've also had our flagship event as well, Women in AI at Entrepreneur First, and also Women in Tech at QuantumBlack last year, and also creating a personal website. So all sorts of different skills there. Another thing that we do to try and showcase the talent of women in tech and academia is we have just started a podcast. It started in January, and we interview women who are working again in tech and academia across lots of disciplines, from computational social science to robotics. So if you're interested to hear more or want to get some inspiration, then please subscribe to Researchers Code on iTunes with the dash, with the / rather, and Researchers Code on Spotify or any other podcasting service. It should be on there. Another thing that we're also doing is that we've got a Twitter account at Researchers Code. So if you've got Twitter, then please follow us this evening. One thing we do is every week we host a woman who works in research to talk about their day-to-day lives and what they're doing in their research. So here's an example of Heather Forsyth, who is doing a PhD at Oregon State University. And we've had lots of people from CERN, people again in the humanities as well. So it's good fun, and there's lots of interesting memes and GIFs, so I would highly recommend following it. All of this would be possible without our team at Researchers Code, so I would like to say a big thank you to all these people here. And Olas is here with us today, so if you want to hear more about volunteering for Researchers Code, then she will give you the best answer, I hope. So if you want to volunteer for our community, so we're a group of PhD students and postdocs who volunteer. You can come and find me during the dinner break or afterwards, or you can contact us on researcherscode.com/join-us. Another thing that we're really keen on doing is that we're quite London-centric at the moment, and we don't really have many other branches outside of London. We've had a few requests of people who live outside London who want events like this. So if you are living outside London, or you know someone at another university who'd be interested in starting a branch, then again, find me at the dinner or contact us at /join-us. It would be fantastic to expand this nationally. Okay. I'm not going to keep it too long, but if you would like to find out more news about our workshops and our podcast, and also if you want to get the slides after the event, I will contact you on Eventbrite, but the slides and recording event, I would highly recommend you subscribe to our newsletter. So it's on our main page at Researchers Code, and you get a monthly update on the stuff that we're doing. Great, so that's it. And also I would like to say a big thank you to all the volunteers who are running this machine learning workshop at QuantumBlack. I think it's going to be a fantastic time. So yes, great. Thank you very much. I'll hand over now.
I like to ask how many of you have heard of QuantumBlack before hearing about this workshop? Great. Great. This is why I'm doing this introduction. So QuantumBlack, the story of QuantumBlack, we were created actually 10 years ago. We are celebrating our 10th anniversary this week, so we're super happy. We originally were founded in Formula One, where our co-founders just met. So it's the story of a data scientist, a software engineer, and a consultant. They were all working in this space, and they were really how much more we could do with data-driven decision and how much more we could improve the performance by just doing some more analysis and using this data that Formula One is literally living and breathing with. It's been really, really successful and a project leading to another. 3 years ago, we have been acquired by McKinsey. McKinsey global consulting company, and for us, it's just been a massive push. So we now serve clients all over the world and across a broad range of industries. So this is just to give you a very brief idea, but we really work across pharmaceutical, healthcare, financial services, and we still work in Formula One. We work with sports team. So the nature of the work that our teams do is very diverse. It's also super exciting because they get to learn about many different industries. But I think what is really particular about what we do is that it's applied. The reality is the world today is all about AI, but it's not ready. So we work with our clients to try to leverage all the data that they have. And it's fascinating because we are using all of this to have an impact now. So it's not abstract, it's not, you know, just in a dark corner of the room being stuck doing some code. You actually have a real world impact. And so what do we do? So we bring teams, and you will hear more about it when my colleague Diana after. We bring teams together to use our clients' data. It normally is a lot of data. We try to identify patterns and to just build solutions, so that most of the time bespoke, to answer any type of problem they would have. So it can be, you know, working on fraud, fraud detection or sports injury prediction, improving clinical trial processes. So it really goes much more, much further than just, you know, financial type of data or, you know, financial optimization. And about QuantumBlack, yay, great. So, you know, 3 years ago, we were just a small company of about 50 people in London. We are now more than 300 around the globe. And we have opened offices last year in Montreal, in Sao Paulo as well. And we are planning to open 2 additional offices this year. So you should hear about it very soon. But it's just been a fantastic journey. And I think that there's only so much more to come. We're just keen to connect and share, and, you know, share the knowledge as well. If you have any question, reach out to us. I will be here as well. Don't hesitate to ask any question or raise any concern. I'm sure the workshop will be great. And if you want to keep in touch, on the website, we put the events that we are doing. So that's just to give you an idea. We have worked on Women as Tech Leaders event in last November. We are actually planning the next edition for May. So it's going to be super exciting. We have done a few presentations and talked about algorithmic fairness, explainable AI. These are topics that are very, very important to us. We have partnered with Women in Big Data for meetups. We also have our own meetup, and you can find more information on Instagram, Twitter, everything that, you know, all the channels, you know. So thank you very much, and enjoy the workshop.
Hello, my name is Jana, and you're just about to start hating me in about a minute, because I'm going to ask you to talk to each other, and we're going to do a little bit of an icebreaker. So welcome to QuantumBlack. There's 4 data scientists here tonight from our team who are ready to walk you through a little intro to machine learning. I say little. This usually in a university environment would take about 10 weeks and a lot of lectures. So there's quite a lot to cover, but we promise we'll keep it interesting, and hopefully no one's going to be asleep by the end of it. So in order to start, can you turn to someone you don't know and just introduce yourself and tell them why you're here, what you want to learn. And some unfortunate people are going to have to put their hand up at the end and tell us why you're here tonight. Interesting reason for being here tonight. And someone please help me, so I'm not sat here alone talking to myself. I'm giving a talk. Guys, someone, okay, yes.
Collectively, we would kind of like basically get on the bandwagon. That's why we're interested. So
Okay,
it's a big thing that we don't know about, and it seems really scary. So
yeah,
yeah.
it is really scary. It's not. We'll demystify it. It's going to be really nice and clear by the end of it. Okay, anyone else? Who shares the same kind of bandwagon? Okay, cool. What about the rest of you? Because you've just done yourself deep now. You need to tell me something else. Anyone? Okay.
Well, my entire PhD is based on it. I sort of dove head first without really realising what I was into, and I just started, so I thought this could be pretty useful.
Cool. Okay. I think that might be a particular case. Anyone else? Okay. Yeah.
Yeah, I'm starting a company in machine learning space, so
Wow.
to
Cool.
see what I'm using.
Very exciting. Okay. Anyone else? Last one.
Last chance.
Yeah, don't rush. I know it's such an opportunity. Yes.
Well, I'm coming from a design background, so I'm in architecture. I'm interested how maybe this could apply to architecture as well. So I'm trying to see are there some parallels. I don't have to code, but hopefully I can learn something.
Yeah, we'll find someone in the room who can help you, and we're all here to help all of you. So let us know. Put your hand through. We're going to go through some exercises. So to go through a little bit of admin, if you can't hear us through any of it, or if you can't see the slides properly, please put your hand up so we know, because that's the easiest thing we can fix. If you have questions as we go along, we're very happy with you putting your hand up and stopping us as we are. It's easier than waiting till the end of the section and asking then, so please do as we go along. And that's all of the house rules. We can go into, hey, this works. Into what we're going to do tonight. So we're starting with an intro to machine learning given by yours truly. Then we're going to have a session on explanatory modeling. Then we have dinner break and more talking to other people. Predictive modeling, and then lastly, model evaluation. So my bit's the only bit without any kind of hard work. The rest of it, you'll have to get your laptops out and code a little bit. We'll be going around the room and helping you as we go along, so don't worry. Okay, so who we are. There's 4 of us, you'll hear from all of us. We're all data scientists here at QB. And between the 4 of us, we have half a PhD, 6-ish MSCs, and some bachelors. But what's interesting to point out is that we come from quite different backgrounds. So we have Roxanne here, who did civil engineering. I did computer science, and then Victoria and Margot did maths and stats. So it's very important to note that data scientists don't all look the same or come from the same background, and you'll see that as we go along, they come from very different paths. In education, there's now a slow trend to introduce data science, but there's no data science proper big degrees yet. So people come from very different backgrounds. Okay, so now that you know our names, here's a few things that you will have heard quite a bit about, and we're gonna present some definitions just to give you some context and to know how to separate these things into mental buckets. So probability theory is that part in maths and stats that deals with random and systematic variation. Artificial intelligence is used very wildly and widely these days. It's a huge umbrella term, but originally it used to refer to machines that imitate what we associate with as human functions, right? So perceiving, problem solving, learning, which leads us into machine learning. So machine learning is an application of AI. It sits under this umbrella, and it refers usually to algorithms that allow computers to learn a task with minimal instructions. So this is what we'll be dealing with most of tonight, right? Lastly, deep learning, and I put this up here because you will hear and you will have heard so much buzz around it. It's the latest and greatest and trendiest at the minute. It's spoken about in most conferences. It's where a lot of the research goes on at the minute. And what it really refers to is processing richer data sets, so dealing with images, raw machine data, and so on. Right? We good? Okay, cool. We'll ask you this as we go along, just to get if we have the right pace. Okay,
And if you didn't get the joke, it's alright.
You'll hopefully get the joke by the end of it, or maybe by 3 years working into machine learning. We'll see. Okay, so as we've said before, machine learning refers to this field of study that gives computers the ability to learn without explicit programming. So why should I really bother with all of this is the real question. And the idea is, this slide's going to look a little bit small, but I'm going to walk you through it. This shows the changes to the industry's core business practices through data and analytics. So you'll see in the dark bubbles that's significant or fundamental change. And at the top, we have everything from travel, media, consumer retail, financial services, basic materials, energy. Every field at the minute is undergoing the data transformation. There's more and more data available every day. So there's a number that I'm not even going to try to read about there. But every day we produce 2.5 quintillion bytes of data. And to put that into perspective, 90% of the data in the world today has been created in the last 2 years. So this is why it's so important to kind of start understanding what these conversations are about, because it's influencing every single field that we kind of operate in. Okay, so what we have here is the Google Trends breakdown on machine learning and data science. So you'll see it's becoming that's from 2004 to present time. And you'll see there's a great interest in this area. It's kind of like spiked up since 2014, 2015. There's a couple of interesting points around why now, right? It's the first time kind of in history that we have all of this compute power at our fingertips, right? Like you can just spin an AWS cluster and do whatever you want with your data. It might cost you a lot, but that's a different story. And there's not just that, right? Not just all of a sudden we have the compute power, but we also have all of this data we generate all the time. All the metrics from your phone, all of the metrics from your home appliances, everything generates data, and these can lead to very important business decisions for the people who are on the receiving end of this data. Okay, so question. You might ask yourself is what can ML do really, and what fields does ML really impact? So there's a few examples here, some more interesting than others. Spam detection, a little bit boring. Fraud detection, much more like complex and interesting if you think. But the interesting thing here, I think, is noting that it's starting to impact all aspects of your life, right? And while if your email ends up misclassified and it ends up in spam or the other way around might not be a huge problem, having a self-driving car make a wrong decision is all of a sudden a much bigger issue. And we're talking about things that are really easily fooled. So understanding how they work under the surface is very important. In the example at the top, you can see a pig, right, labeled correctly by an image classification algorithm. You distort the image a little bit, and you have an airliner. So this is funny as it is, but when this translates to you getting rejected for a house mortgage, then things become far more serious. There's a lot more legal implications. There's a lot more to deal with, like explainability and opening the black box in there. How are we doing? Cool. Okay, so here's a few examples of the things we've done at QuantumBlack and kind of the areas we operate in. Fanny has told you just a little bit of what we do. But we do a lot of work in pharmaceutical, so we're helping pharma companies get their drugs to market faster. Traditionally, these processes used to take years and so much, and these companies sit on a lot of data, so it would be great for them if they could just speed up and get their drugs to market faster, helping patients. We still do Formula One, so that's combining image processing techniques to design a new way of measuring pit stop duration, so kind of accelerating an already super competitive sport. We still do basketball, we still do all sorts of other industries. A lot of more information is on our website if you really want to find out. And right, the other thing to note is that this isn't just for data scientists. So if you're sat here and thinking, right, I don't exactly want to do all of this, or I don't want to do machine learning, I don't want to be a developer, I don't want to write code, it's not important just for data scientists. So in the way we work here in kind of data science consulting, it matters for everyone in our teams to understand what happened, what's the process, what's at the other end. So we have our designer, so we split this into kind of the technical people who deal with the data and actually get to code. So you'll see their data engineers, you'll see machine learning engineers, data scientists, and then you have the people who deal with the experience and the client engagement. So you'll have designers, client service leads, strategists. All of these people need an understanding of what's happening under the hood, because otherwise our projects would just fall apart. So my argument is that, yeah, it's great to know about all of these things, but I guess that's why you're already here, so we'll roll on. Okay, so what do data scientists really do? Because they're the people to mostly use the machine learning techniques. So a data scientist uses advanced analytics to solve complex problems. So we'll see a problem in the real world, or it will be flagged to us, and we'll try to find the best techniques that we have available to kind of deal with this. Agile data science involves kind of sprints and iteration. It's closer to like agile software development. It moves faster, and it also implies failing fast. So we won't always get it right the first time, but the quicker we kind of learn from it and evolve, the better we are. So this is how the process of data science looks like mostly on our side on a client project. And I'll give you a little bit of a walkthrough through this. Can you see her at the back, roughly? Okay, cool. So we have the raw data, and sometimes we won't even know if the kind of data we need exists. So we usually go to our clients, they give us a problem, and we'll have to kind of dig through, ask around, find the right data sources. And you'll see this happen in any sort of data science project that you do. It's really, really important what you put in. So you get the raw data. The raw data then gets aggregated into things that make sense, and Roxanne's going to walk you through exactly how this looks like on a data set. So we're going to take this from like abstract and fuzzy and on a slide and put it into a real data set. And then it kind of becomes, so this is more of the data engineering realm until aggregating data, and then it becomes a data science role. So you'll see the big element here is a loop. So as I was saying about failing fast, you're not going to get your data science model right the first time. You're lucky if you get there in like 10, it usually takes more. So we try to reduce the number of variables, select the variables, check our modeling, what type of models we want to use, look at insights, compare, discuss with the client, start again. And we do this over and over again. And at the end of the project, we'll deliver something. So it can vary from just some insights to a kind of full-fledged solution that they can use forward. So this is normally what a data science project looks like, at least in consulting. Any questions? Okay, cool. So what do people use normally to do data science? So we'll be using Python mostly today. You have here things that come from the software development world. So you have version control systems like Git. You have programming languages like Python and R. You have all sorts of development tools that help you stay organized and make sense of your code, like PyCharm and Jupyter Notebooks and so on. And then when you reach kind of the limits of what your computer can do, when it starts taking 7 hours and it's starting to like fan really loudly, you have to move into the distributed computing world, into cloud computing. So you'll have Spark and AWS and Databricks and the kind of large scale solutions to do this. Yeah, there's also like the data platform, the ML and AI tools. So you'll see the logo for TensorFlow there in the corner if you're doing kind of more fancy, complicated things. Right, so we're gonna go through this a little bit slower, and I'm gonna ask you to put your hand up if you've kind of heard of these splits as we go along. So first of all, we have supervised and unsupervised learning. Cool. Okay, perfect, thank you. Univariate versus multivariate. So this is, do I take one variable or more? Okay. Linear versus nonlinear. And regression versus classification. Cool, okay. Perfect. Thanks for that. So I'm not gonna dwell on it very much then, given that most of you have heard these concepts, but we're still going to go through the definitions for those of you that haven't. Supervised and unsupervised, with an example with ducks. If you have a data set that has labels, so in this case, the animals on the left have a label of duck or non-duck, then you're in the space of supervised learning. You have something to learn from. Basically, there's an existing label there. On the right-hand side, you'll see that we have unsupervised learning. So the algorithm will not have labels, and you'll have to infer some structure hidden in the data. So here, it will have to learn what the duck looks like, and that all of these ducks kind of fit together in one bucket, and the rest of things don't behave the same. Okay, regression versus classification. So this kind of comes to the question of, what's the phenomenon that I'm trying to predict? And am I trying to predict a continuous variable? So in the regression question, if I ask what is the temperature tomorrow, you can tell me a number between, should I put this in Celsius, anything on that axis, but it's a number, right? It will be something on that axis. If we have classification, we're talking more about bucketing things. So we'll have, will tomorrow be hot or cold? Will it rain or not? So that's how that works. We good? Okay, and then into more of a complicated kind of split of things. We have 3 ways of looking at problems generally, and then the algorithms that we use kind of flow from that. So you have explanatory models. In this case, you want to understand, gain insight from historical data. And the models you have in here are causal inference, correlation and factor analysis, clustering and segmentation. You also have predictive algorithms when you're trying to, say, predict ahead what's going to happen, right? And in those buckets, we can have linear regression, neural networks, random forest, all of these algorithms that you may have heard about already. And then there's also prescriptive, making decisions to kind of gain an advantage. And in there, you have simulations, recommender systems, based on kind of historical preferences and optimization. However, we have grossly oversimplified things on the previous slide. The world looks far more complicated than that, and these algorithms kind of can slide in between the buckets and move across the axes. So it takes a little bit more of an understanding of what their true powers are to see what you can really do with them. Okay, so that is pretty much it from me. We're going to walk through exploratory modeling with Roxanne. Yay! Thank you.
So let's talk about explanatory modeling. So 3 things on the plate for explanatory modeling. First thing, feature engineering. So that's the first step. Second thing, PCA. How many of you guys have heard of PCA? Cool, nice. What about K-mean clustering? Good. And so this works in a very interactive way. I'll let you guys imagine you are a data scientist working at QuantumBlack, and then one day receive a data set, which is London Underground entrance and exit data set, which is 3 columns. Very simple data set. But there are so many information hiding in that data set. I would like you guys to work in pairs and then think about for 2 minutes what kind of information can you extract from that data set. I'll give an example first. For example, like hourly flow, people flow from, I don't know, Westminster Station, that kind of stuff. Can you guys work in pairs?
Action of influenza level in the London boroughs, and we compared how influenza spread in London.
That's it. Cool. What else?
I was thinking it's perhaps a bit more removed, but the population that's tapping in and out, where they're coming from, so you could assume by the time that it's their home versus where they work.
Yeah.
Like that.
So you can infer from like
Commuting.
yeah, commute. Cool.
How much time they spend at work, essentially, all these patterns.
Fine.
Sometimes traveling. Or even at work.
Maybe work. Cool.
The length of the commute at different times.
Yeah, commute.
The relationship between people, if some people enter at the same time and exit.
The pattern of travel.
Wow.
Any more? Maybe one more.
We maybe look at how many new cards have been issued in a certain period, or like how many new
new cards.
users.
You mean Oyster card being issued?
The card ID, the card IDs, new users. Yeah.
Cool.
If there's like a period of immigration in the area, I don't know.
Yeah. Cool. So we have a lot of features right now. And the first thing to bear in mind is the ultimate goal is to build a table that fit into your model, right? So we need to introduce some kind of spine on these features. So usually the spine will be, for example, if we want to look at station level and width time. So basically you chop the time into chunk, and then with each station, and you have different time, right? Because this is one single timestamp. So that's the thing to bear in mind. And secondly, we need to think about the granularity of timestamp. So how large do you want to crop the timestamp? So that's the second thing. So good job, data scientists. You've come out of a list, for example. We have so many data scientists who come out with 300 more features. And so it is not possible to fit all those features into our model. So therefore, we introduce feature selection. But why all those features cannot fit into the model is because, for example, it will cause overfitting in some scenarios. If you haven't heard about overfitting, Victoria gonna explain later on. Yeah, but bear in mind, so it's gonna be overfitting, and it will drag your accuracy of your model, and also based on like limited computational power, so it will like hugely increase your training time for the model. Then we have feature selection that are there are 3 main methods for feature selection, and the first one is called filter method. So this one we use very traditional statistical test for our features. As you can see here, so that's a correlation matrix plot in a heat map. So from here we can tell the univariate collinearity across all the features, and then we can do our first filtering. And also filter test is really good at dealing with sparsity. Did you guys heard of sparsity? So sparsity, for example, imagine if a person with Oyster card, and that Oyster card is linked to a very rare roll card, and may happen 1 in a million. And if you build a flag based on that rail card, it's going to be super sparse if we have a lot of like data. So the variation based on your targets will be close to 0, which is not very predictive in our model. So that's why we tend to throw out those features, and we tend to keep those important features to our modeling. And moving on, we have wrapping method. So this method select a subset of features, and then it fit into the model, and it runs the model, and you get the performance. So based on the performance, you decide if you want to add more features or throw out that subset of features. And finally, we have embedded method. So this one is the model has its own feature selection method built in. This one, think about random forest. So random forest, we have variable importance, right? So that's an example of embedded method. Cool. So let's say we have identified our problem. We have 500 plus features that has high collinearity and multi-collinearity. So what would you do to get to the master label? So are you guys familiar with the term collinearity? No? Okay, cool. So collinearity is basically when you have one feature and you can use other features to represent that feature. So that's collinearity. And because we have, for example, 500 features, that's a lot. And we have sparsity because we built so many flags. And apparently we have collinearity and multi-collinearity. And what should we do? So in order to filter 500 features, it's really hard to fit all those features into one model and then run it quickly because we have a very large data set. So first, we need to do the filter method, which removes the variable with 0 or low variance to remove the sparsity of the features. And then we put into a correlation matrix, which you can identify which 2 features are highly collinear. And then you remove all those, like you select one and you drop the other one. And so for multivariate collinearity, so here we use variance inflation factor. Any of you guys heard about variance inflation factor? Okay. So it's a method that helps you to drop multi-collinearity features. So how does it work? It basically selects one feature and then you use other features to build linear regression based on that feature. So that, for example, your x1 will be a y, and then the rest of one will build linear regression based on this one. And you calculate the R-square score, which is the goodness of fit. And if the R-square score is 1, that means you are highly collinear, which means other features can represent this feature, which means this feature can be removed. So in this case, variance inflation score will be infinity. So if you loop all those features again and again, you basically filter out all those multi-collinear features. Make sense? Any questions?
Can you just explain a bit more what you mean by sparsity?
Sparsity.
And why is it a problem?
Why is that a problem? So if you have so back to the rail card thing. So if you have a really rare rail card, or maybe think about a disease, for example, and there are many people have, for example, obesity, right, or sleeping problems, but not many people, for example, have depression. And if you have a data set of 1 million rows, right, and then you build flags, for example, if that person has depression, and only 1 people in your 1 million data set has depression, and then if you look at that model and your ultimate prediction, for example, is obesity, if given that person have depression, if that person will have obesity, and if you look at all those data sets, the mean will be 0, right? So if you fit that feature into your model, that won't be very representative. And
so you just remove that variable?
Yeah, just remove the variable. But bear in mind, we have like 500 plus features, and we have 1 million row, for example. So based on like computational limitation, we cannot put everything inside the model. Yeah. Any other questions? Yeah.
Is collinearity something like we can represent a day by like 24 hours, so we don't need to use day and hour separately, so we can just do hour and then do something with that? Is it something of the sort? Or?
Yeah. So in my recent project, we've built features based on different time windows. So people will build, for example, if the person have a kind of disease, looking back ever. So the person ever appear in the data set has that disease, we build a flag. And then we also looking back 1 year window. So those features we find very collinear with each other. And then that's going to cause a problem to the data set. So we run this to basically drop all those features. Yeah. Yep.
So isn't sparsity an issue then to do with data acquisition rather than your model? So would the solution just be get more data?
True, but most of the scenario, I mean, the world is really brutal. So in most scenario, we just cannot get more data. So yeah.
How is sparsity different to it being like an outlier? It is an outlier then, essentially. Or it won't correlate to what you're trying to predict. It's just not going to help your prediction anyway.
I think sparsity is in general.
No, it is not actually about the outlier itself, and it's not only the issue of not having enough data. Let's think about the features that are intrinsically, related to very tiny population, right? There is like really some very rare disease that appears only in 0.00001% cases, and this is exactly the very sparse scenario, right? And that is why this person is not the outlier itself, right? But it's just the case that there is like a very rare event that might happen. And also, if you think about like some categorical variables that can, right? Categorical variables, right? And you have like a lot of categories. Let's say like the country where the person comes from, right? And you want to say that, okay, does this person come from this country or that country or that, and so on. And so you're gonna have like, I don't know, 160 different columns, and only one time, only one row is going to be 1 and the rest going to be 0, right? And that is why your whole matrix will be full of zeros, and only tiny fraction of those cells will be populated with 1s. And it means like when you're gonna build your model, it will, like I don't have enough ones to learn about it. I don't know what to do with that. So that is why the sparsity is the big issue. Sorry.
Thank you.
So it's something that the model doesn't benefit from, basically. I'm sorry. It's something that the model doesn't benefit from, basically.
Yeah.
So like there's no point using it because it's almost not a real life situation. So we just get rid of it. It's not useful to us, basically.
Yeah, sorry, just like my background, and I have this professional information, so we're gonna talk about sparsity. Yeah, so one of the things that people normally do with the sparsity issue, they might want either to do it to group your variables that you have, and maybe you take this very rare disease and you think, okay, it's very similar to this one which occurs more frequently, and then you group it into this bigger bucket. Of course, you lose a bit of information, but you don't have this 3 people in 1 million that will not give you anything. Or on the other hand, what you can do, you can actually run some sort of very well-known dimensionality reduction techniques, one of which is PCA, and Roxanne will present you this. But this is some sort of trickery that we can do on top of that. Sparsity and big dimensionality is our enemies, right? Okay. Thank you.
Cool. Any more questions? Shall we move on? Cool. So, given that situation, we run a lot of feature selection algorithms. Now, we shrink our dataset to 150 feature. That's good, but still too many for our model. Then, in that case, how can we obtain most of the information whilst reduce dimensionality? So here, PCA. So PCA is a method to, as you're going to know, to reduce dimensionality. And how does it work? So basically, think about you only have 2 features, and you have all those points, and you fit your line. It's different than linear regression because this line is used to maximize variance. So in this case, this one is how you fit the line, and for PCA, and this one is linear regression. So you fit differently. Let's say you have fitted the line. And then the second step is to shift the origin. This one is the mean of feature 1, and this one is the mean of feature 2. This one, you shift this smiley face back to the origin. And then you have your PC1. And PC2 is perpendicular to PC1. Cool. And third step is to calculate the variance of the plane. So in this case, first you need to rotate the plane and ignore the original axis. And so how you calculate the plane, it basically is the square residue distance from for PC1 divided by m minus 1. So in that case, you can calculate the variance. And if we get the variance, we can also calculate the total variance by adding those two together. So in this case, let's say we have variation for PC1 is 18 and variation for PC2 is 5. And in that case, we have 23 for our total variation. And PC1 in that case accounts for 78% of the variation, and PC2 accounts for 22% of variation. Think about it as information contained in those PC. And we can also plot the discrete plot, which will tell you the cutoff point. When you cut off, for example, which point can you obtain most of the information from the PC. And so think about, you have M more features. You do it exactly the same as this way. And you plot your discrete plot. You find the elbow, you get the cutoff point. In this case, let's say the cutoff point is 3. And so which means your PC1, PC2, and PC3 can account for most of the variation in the data set. So data projection on those 3 dimensions is a good approximation for the entire data set you have. Cool. So let's say we finish PCA and we want to observe how different station performs based on like people flow. And a quick way of doing that is to do k-mean clustering, because it will group the cluster station together to observe like they share the same information. And so how does k-mean clustering works? So basically you have begin with random centroids, and you assign each closest point to the centroid. And then you move the centroids into the group of assigned points. And then you assign each point to the closest centroid again. And then you move the centroid again. Again and again, until there's no reassignment. Then you stop. Cool. So k-mean clustering is good at, for example, you can see it's very easy to use and explain, and very easy to visualize. And it works really well with large data sets. Also, it's very widely applicable to all data types. And it can also lead to non-obvious insights. So it's one of the most important tools for explanatory analysis. But also, sometimes it can be a bit tricky to find good clusters, and it can be really hard to interpret results. Yeah. So that's pretty much it. Any questions about k-mean clustering and PCA?
I didn't understand this k-mean clustering. Would you mind, even if it seems very simple, I've never heard of it.
Yeah.
I can see how it works for like some data about location, but I'm struggling to think about different data analysis.
So group the features of same behavior.
So let's say that, okay, let's just assume those are the station. How do you start with those 3 mean? Is it a random? How do you start with this 3 big blocks?
Manner to assign centroids to these.
So how do you start with putting the centroid? That's why.
Random.
Okay, it's random.
Yeah.
Okay.
Random. Yeah.
So if you rerun it a couple of times, you'd end up with completely different clusters at the end of it. it's not like an absolute truth because you're starting randomly. You can.
It's never an absolute truth. We live in the random world.
Hence the nudging in that.
How do you choose the number of centuries?
There's a plot, there's an alpha plot, and basically it's the alpha plot. We find a cutoff point. It's similar to PCA. I'll introduce it later to this in the tutorial. Yeah.
So is the point of it simply just to find data that's similar to
Same behavior. Or maybe group them into clusters. Yeah.
on random? Actually, it's the categories you cluster them in are completely random.
What do you mean by random? You assign random points to it, and then you study the clusters.
Yes.
Yeah, and then you interpret.
Each time you do it, it's different.
Yeah, but you sort of the similarities of that data. That similarity you look at is essentially something random. Like a random property of the data.
To this randomness thing, right? About this random initialization, right? So you start with some random centroid, you just throw 3 points here, right? You decide, okay, I think that it's going to be three clusters here. I throw these 3 random points. Then you run your algorithm. It converges to some clusters and finds some clusters due to this, similarities you said, like closeness in terms of some distance, right? So close instances will be in the same clusters. And just to answer your question, the previous question about is it complete randomness, right? It is sort of a random outcome, right? Because you started with a random initialization. But normally what people would do, they would maybe start several runs with different random seeds, right? To kind of try to mitigate these risks. And normally, if your data actually has those clusters intrinsically, you will end up at having the same clusters. So this is what you hope to have.
But it might not happen. It might not converge, and this is one of the weaknesses of this approach.
Absolutely.
And as Victoria mentioned, you do define a distance. So I'm sure you're all aware of the Euclidean distance, right? The square root distance between points. So this is one we typically choose in some spaces to minimize distance between points in a cluster and maximize the one between clusters, right? So this is what the algorithm does. There are other distances which are much more sophisticated, which are used like in natural language processing when we're trying to measure, for instance, distance within words, between words. And we also use clustering in this type of use case. So it has very broad applications, and the adult data set, which we're going to show it on later on, actually quite soon, is one of them. But
like right now.
And also the randomness thing is like the picture in the first slide, right? I was saying, and you're going to understand this as we go later on. It's like you shake the bag and it spews out something else, and you shake it again, and in the end you'll have to aggregate those things and see
if you don't like the result, you just try another random seed. If it's better, it looks better. Yeah. So this is why people say that data science is about art.
So when people accuse us, it's not a science.
Jokes aside, really, we do have this sort of methods to beat this randomness. So this is exactly trying to start different initializations, trying to do this, and robustness is a big issue, and we're going to cover it in the tutorial as well.
Cool. Any more questions? Yeah.
So number of clusters you said is decided upon the elbow
plot.
Elbow plot.
Yeah.
You showed us an elbow plot for the PCA as well. It's
Yeah.
the same one. That was 3 as well.
It's different, but the idea is similar. Basically, PCA is so here. So this means each of, for example, the number of PC accounts for different variations. So think about eigenvalues as a variation. And then you can see plane 1, 2, and 3 accounts for most of the variation. And then those accounts for smaller value of variation. So in that case, if we want to obtain most important values, while you don't want those features, you can just take from 3, because those 3 planes can contain most of the important values. Yeah. Cool. So moving on, let me introduce you to the adult data set. So the adult data set is available from UCI Machine Learning Repository. So you guys can download it and play around when you get back home. It's completely open source. And the data contains personal information like age, education, work class, occupation, your marriage status, and your ethnicity. And also is, so here, sensitive attribute gender. So it has female or male. So it's kind of against fairness. And so our target variable is salary. So there are two categories of the salary. So it's either larger than 50K or smaller than 50K. And the train set has 32,000 observations, and the test set is 16,000 points. And shall we move on to the tutorial?
It should be great. So, first of all, thank you, Roxanne, for your nice talk about exploration of our data. And once we know our data set inside out, you know, everything about our dependent variables, we might be actually interested, you know, this is not enough for me. I want more. I want actually to use my data to predict new unseen labels for the target variable. So let's remember our example from the exercise, right? We had this income variable, and let's say that, okay, now I know, like, you know, BCA, means, blah, blah, blah. But what about someone that I don't know the education, I know the country he comes from, I know all these features that we collected. What about this person? Can I actually predict what income this person gonna have? Will this person make more than 50K, or is this person a loser? So this is why actually we have all those nice models, machine learning models, and that is why machine learning is so cool, and we have this company and everyone is so excited. This is exactly why we're here, because of this predictive power of machine learning that we have. So yeah, I think that it's better actually to listen to what I'm saying than to looking at the slides. The $1 million question is here, right? We want to make sure that we understand all the underlying patterns of the data. How do we capture it? So that when we see some new instance, we can do this prediction. So in this case, you might have like a very, very simple model, which is terrible because it doesn't give you any reasonable predictions. And in this case, we have the problem of underfitting, as we call it. On the other hand, what might happen is that you have a very cool, sophisticated model that captures all the little dots here, and you know, when you show some point from your training data set, it predicts this very exact number that you have. But the problem is that when you have something new and unseen, it predicts you a crap, and it is not general enough. It just captures the noise from your data rather than the structure, the underlying patterns. And this problem is known under the name of overfitting. So what we want is to find this really nice sweet spot, something between this underfitting and overfitting, something simple but not that simple. Right, and this is actually the art of machine learning. The idea here is that machine learning techniques exist to overcome this issue and to beat this underfitting and overfitting trade-off. And they are called like normally train cast split, or like more sophisticated things, more advanced things like cross-validation, whatever. Just to explain you the concept. So, how many of you are familiar with a train cast split? Please raise your hands. Okay, so cool. The idea here is that you have your data that you are happy to use to make predictions. But the problem is that, once you train the model, you're not quite sure if you actually overfit it, underfit it. I just trained it on the whole data that I had. So how can I actually measure if it's good when I do this predictions for the unseen data samples? That is why we can actually kind of pretend that we don't know the part of the data, right? So we can split all the data that we have into two chunks, right? Like training and test. Training will be the bigger chunk because we need enough data to train our model, right? And testing is the small chunk on which we're gonna evaluate our model and see if we actually learn those patterns or structure in the data or not. Make sense so far? Okay, very well. And you can say that, how do I split this data? I do it randomly. Randomness is not that good because I cannot trust it. Maybe I should do something, repeat this splitting. Maybe I should, do these sort of things to build this randomness. And that is why there are these concepts of cross-validation and so on and so forth. So, but the basic idea is the same. We need to pretend that we don't know the part of our data to be able to evaluate our model on these data. Okay, very well. Now we know that we should not overfit, we should not underfit. But some very smart data scientists from QuantumBlack came to you and said, like, I know a lot of models, like single learners, simple ones, logistic regression, decision trees. I know, more sophisticated single learners, like neural networks, support vector machines, whatever. And then another senior data scientist comes and says, no, guys, this is not enough. I know ensembles. I can actually combine those models and get some results. And here you have all this variety of models, and sometimes you don't know what to use. And also, you face another trade-off. Some of those models are simple enough and therefore intuitive to interpret the results, but give you not the best performance that you can achieve. And on the other hand, you can have those very sophisticated, very highly performant models that actually are very black box-like, and it is really hard to explain what is going on under the hood. So that is why you actually need to think what is the priority in your case, right? Do you want the performance? Do you want the explainability? And sometimes this decision is made by the business logic, but sometimes you have constraints that actually do not allow you to use those models that are not interpretable. Let's say in the banking, you are not allowed to use neural networks because of this black box thing, right? If the person is not given a loan, I have to answer why, and I have to give, these are the rules according to which the person is given a loan. And neural network just doesn't provide these rules. Very good. Oh. So, just to give you a gentle introduction to the world of those models, as I promised you, I will introduce logistic regression, decision trees, and ensembles. And we're going to start with the simplest thing, which is logistic regression. So again, you remember? I remember that you actually raised your hand and was asked, and the difference between regression and classification problems, correct? Like in the regression setting, you have some sort of continuous variable, and in the classification, you have labels, either like binary labels, yes or no, or some several labels. So simple linear regression, where for is regression tasks, right, where you have continuous variable, and it makes the assumption that you have your independent variables that can be combined in a particular way, like linear way, that can be adjusted in some way that they represent your target variable. So let's say you have a bunch, 100 independent variables. You're going to assign every variable a particular coefficient, a weight. Then you're going to sum it up, and you will hope that this some will be close to your target. Make sense? Okay, so this is like a very strong assumption that you can linearly combine the independent variables to get your target with some noise. This is good, this is fine, okay, continuous variable, we have this line, we have the slope, very well. What should we do if we have a binary variable? I can draw this line, right? But I'm not sure that it's very helpful. Simple linear regression doesn't work in the binary case, eventually. Agree? Yeah, I think so. That is why you should actually think about some sort of trickery that you can do to kind of, do it more binary, but still continuous. That is why machine learning has this sort of what is called sigmoid function. I'm sorry for this. It's called sigmoid. So you have this formula, which just squeeze your linear function into this, I don't know, something, this curve, right? And now you see that it's very close, like to 0, 1 threshold-like function, okay? And also, when you get some x, you get some value between 0 and 1, which we interpret as the probability of a positive label. And you set a threshold which says you, okay, if I get the p with this value below this threshold, it's going to be 0. The prediction is going to be 0. And if it is above this threshold, the prediction will be 1, right? And it's up to you actually to decide where the threshold is going to be. So for most of us, it's kind of very intuitive to set the threshold at 0.5, right? Because it's very fair. But some people from fairness department will come and say, actually, it's not fair. Let's adjust the threshold to b. Maybe for some people, it's really hard to put this threshold on 0.5 to get a positive outcome. So that is why it's up to you as a data scientist, up to you as analyst to set this threshold. Well, we're done with linear regression, some blah blah on this. And then you are like, okay, I have this very strong assumption about linear combination, the fact that I need to linearly combine my independent variables. It's a very strong assumption, by the way. World is not linear, and sometimes it's not enough. The dependence between your target and the feature that you have might be non-linear, and you should think about how to actually overcome it and what model you can present that would tackle this non-linearity. And this is why I decided to show you decision trees, which is the state-of-the-art linear algorithm, which is also very intuitive and gives you a very high level of explainability, which is very important. Also, no need to read it, because the best way to learn something is to see the full law in the figure. So let me actually go with you through this plot and show you how decision trees work. So let's say we have the problem. We need to decide whether or not to satisfy the insurance claim. Okay. We have a guy who came with a lot of his data and also socio-demographic data, his past history with insurance, and so on. And you want, to actually decide whether or not we need to satisfy this claim, right? Very real question for the insurance companies. So in this case, what you can actually do, you take all the data frame that you have, all the data for all the customers that you have, and what you try to pick a particular variable and set on this variable a particular rule which will split your data set into 2 groups. And what you aim for is to get very pure nodes, very pure subgroups in terms of this final output that you're going to have, specific target, whether or not the person will be satisfied with this insurance claim. So like here, if we go into details, it's gonna be related to the entropy and information gain and some very fancy stuff. But what I want you to think of is you have some sort of the rule on the variable that splits your data into groups in such a way that in one group you have like a very pure, the group is very pure in terms of the target variable, and the other one is also very pure. And you try to kind of maximize this information gain from the feature and split it nicely, and to maximize the purity of the nodes that you get at the end. And so you not only can do it at the very first level, but you can continue this procedure recursively, going down this tree and having these splits for subgroups over and over again. Are you with me? So far, so good? Well, so in this example, what we have, like refund. Let's say we have this historical data about guys, and we don't want to know actually what this person refunded in the past. And we say, okay, if yes, it's most likely that in this case, we also need to satisfy this claim. But if not, we need to go further and investigate more whether or not we should satisfy this claim. So we go to this variable, no marriage status, which happened to be very important. And we split it again. For married, don't satisfy. For single divorce, maybe satisfied. And you go over and over again, deep into this rabbit hole. So, is it clear? Is it cool? It is, because you have those rules, right? And if a person from somewhere comes and says, why was not satisfied with my claim? You can say that, you know, I'm sorry about marriage, so that is why. And like this, you can have very nonlinear rules, after all. You cannot represent it as a logistic regression. But you have very explainable, very highly explainable. And this is very cool. Okay, some words. But, some words more. But we will share all the presentations, no worries. I just don't want you to read this white on black slides. So, this is good, right? We are so excited. Decision trees, let's all apply decision trees for everyone. Fair enough. But, one moment. There are some challenges. One problem with decision trees is that if it is not tuned well, it is very prone to overfitting. So you can actually end up with a very deep tree with a lot of little rules in it, and overfit a lot, not generalize enough. And this is a problem actually. Second thing, it's a greedy approach actually. When I showed you the case, when it's married or when it's not, this is a feature that we need to have here. But actually I didn't tell you the truth, right? We need to select this feature to appear there to make this rule. And this is done in a very computation consuming greedy search way. So I told non-robustness. A little tweak in your data can change the outcome if your decision tree is not in this sweet spot between underfitting and overfitting. So that is why we need to think, so what should we do with our decision tree to make it better, right? And that is why people were like, what if we actually combine several decision trees? It kind of worked with parliaments and the election bodies when we decided, one person can be actually very erroneous because people are full of flaws, as they say, and you might think, okay, if one person is not perfect, then maybe if we have 2 or 20 of them or 100 of them, and we average their decisions, maybe it's going to be better. And so far, it works fine, okay? Not to let the most recent events. And this idea actually replicates very nicely in machine learning with decision trees and other models being combined. The idea here is to take several models, give them subset of your data that you have, and make them learn on those subsets. And then what we do, we need to decide, okay, let these guys vote or let average somehow the result that they give us. This is basically the idea of ensembles. Yeah. And when you have this ensemble trained, and you have a new data point to come to you, what you're gonna do? You're gonna go through all your learned models, your trained models, and you make them vote, or you kind of need to average and decide. So if this model says no, and this model says yes, and a bunch of others says no, and then yes, what is my final decision? You need to come up with some sort of voting rule. You can have a majority rule, or what people can think of, or you can just average and set another threshold, whatever. You can have this voting rule and a final prediction of ensemble. Great, very nice. But it's not the only thing that you can do with models, multiple models, right? You not only can make them work in parallel, right? So the thing that I described was very much parallel. So I have all those models, I gave them all subset of data, we learn, cool, very nice. What you can do is to actually make models help each other and make them learn in a sequential manner. So we know, again, that the models as people are not perfect, but maybe if they help each other, it's gonna work fine. So this is exactly what boosting does. Yeah, by the way, the previous approach was begging. Boosting, what it does, it says, okay, my first model, take this subset of data, it learns something, it is not perfect, we know, but what I can do, I can actually make my next model to learn something that was missed by my previous model. So I kind of impose some sort of high weights on the misclassified predictions. And then iteratively, it's gonna work like this. Every next model will help the previous models to learn something new that they missed before. Sounds very good, but it doesn't make any sense so far, right? Let me actually show you the example with yeah, just like it. A random forest is alright. We're gonna see it. This is not that important. You will go through it if you want to have more details. For boosting, as I described, right? Let's say we have three model in a sequence. First model, the first iteration, what the model can actually do, it's only to draw the line with perpendicular line, either a vertical line or the horizontal line. This is the only thing the model can do. It's a very stupid model, but we're not going to charge it because they're going to work together. And the first model did some mistakes with these guys, right? The next model is like, okay, I know you struggled with them. I will help you. And it gives a very high weights to those misclassified points. And then this new model, what it's going to learn? It's going to learn new decision boundary, right? And the third model comes and says, I know you struggle with those minuses. I'm going to help you. And draw this line. Then, according to your algorithm, you know how badly or how good your models performed. You will give them some weights. It's also like your algorithm in charge of those weights. And finally, you will summarize it all and have the final classifier, which does really well. Look at this guy, it's incredible, right? Because it classified everything correctly. And together they did the job. Very nice. And this is boosting. Is it clear? Great. Some words. And examples of boosting algorithms. There is a meme, a joke among machine learning practitioners that like XGBoost, import XGBoost, XGBoost dot fit, and you are machine learning engineer, data scientist, whatever. It is a joke, but as every joke, it has a lot of truth in it, right? XGBoost is the algorithm which is maybe the most performant in this, if you know, Kaggle competitions, like the open competitions for data scientists around the world. And yeah, it works good, but you actually need to set all the legal parameters and to make it do the job right. So I just want you to understand how important this boosting thing is, and that there are several implementations, several possible algorithms, how you allocate those weights, how you actually, you know, make this next model to know that I need to concentrate on those misclassified instances rather than that, and so on. So yeah, the most known of them are Eta Boost, gradient boosting, XGBoost, Cat Boost. Less popular. Let's forget about them. Not going to have our attention. But for those four of them, it's a big thing. It is all in nice packages that you can download, import, whatever, and do your job. So thanks everyone for listening to this part. And now we have an exercise.